Okay, this is part 2 of the software video series. Apologies that the audio is a little bit light. I've got the microphone gain turned right up on the laptop, but for whatever reason this screen capturing software that's built into Windows 10 is a little bit quiet. So in the last video we looked at the hardware. We looked at typically the pins on the Arduino that we want to use for the I2C communications, as well as the rotary encoder and the push button switch that goes with that. And then we looked at the example crystal frequency, or the crystal filter, and there where we want to place or how we want to set up our variable frequency, and then after that the beat frequency. So based on that, let's just run through pretty much sort of line by line the software, and hopefully it'll sort of start to make sense. So before I look at sort of some of the pin assignments and the like, I just want to sort of go down here to the main loop. The way that the Arduino works, or a lot of, well, in fact most software works in this particular case, is a loop, and this loop just runs forever. It just goes round and round and round, runs through, gets to the end, goes back to the front, runs through it again, and over and over and over again. So this is a very simple program. So all it's doing, and we'll look at the code in a sec, is has my frequency changed? So is my current frequency not equal to the old frequency? In other words, you've rotated that rotary encoder and you've forced the frequency to change. If that is true, then update the display, in other words, to display the new frequency, and we'll see that further on down. Send that frequency, in other words, tell the Si5351 to update itself, and then make the old frequency equal the new frequency. So therefore the next time through you can see if something's changed again. And the only other thing that this loop here does is then just checks to see if that push button switch on the rotary encoder has been pushed. And if it does, and we'll come back to it, it will update the display. So that's all it's done. So that's essentially what the program's doing. And then in parallel with the loop going around and around and around in circles, is what's called the interrupts. So if you were to rotate that rotary encoder, that'll set off the interrupt service routines to then go and actually change the frequency. And once that's changed, then this part of the main loop, which is looking for a change in that frequency, comes into play. So that sort of just sets the scene a little bit. Right, let's go back up the top. So first things first, in the software we need to include the applicable libraries that's needed to sort of make this program work. So I won't go into in this video what a library is. There's certainly plenty of information on the internet about what that is, but essentially there's just other programs and other data to enable this program to work. So we need to have a library called wire.h to allow us to do the I2C comms. We need a library called liquid crystal display underscore I2C, and that's the library that's needed to talk to that 16:2 LCD display. And in this particular case, when we looked at the back of it, it's the I2C version. So we need a library that does some interpretation and some interfacing with that. And we also need the library, the Si5351 library here. Now I use a library from Jason Mildrum, and I don't think this is going to come through on the capture, but I'll just talk as I bring it up. If you were to go into onto the internet, you would search for a guy called Jason Mildrum, and you should be able to find his Si5351. I have found that to be the most reliable, for me, library for talking to the Si5351. There are other libraries out there, but like I say, that's the one that's certainly worked for me. And I just want to do another little caveat on this chat here. There are many different ways of structuring software. This video here is just looking at how I've done it. It is certainly not the right way. It is a way, and it's just a way that sort of works for me, so I sort of just stick with it. A lot of the radios, it's the same. It's the same old. The only thing that sort of really changes is the data that I'm displaying on the screen. So, like I say, this has been working for me for quite some time now, so I just stick with it. So, continuing down, we've loaded up the top there the libraries, and now we have to define our constants and variables. So, we've got a few constants. At the moment, I've set up this particular example to be a general coverage HF receiver, so that the lowest frequency that I can drive the Si5351, I've notionally set to 1 MHz. I could change it, of course. And then the band end, in this particular case, I've set at 30 megs. If you wanted it to be, for example, just an 80-meter radio here in New Zealand, then I'd have band start at 3.5 megs and a band end at 3.9 megs. You also, I've set here an initial start frequency, which is band initialization. Now, I will say I'm more than happy for this software to be shared, and I can put up on my blog for it to be pulled down. So here we set our lower sideband, in this particular case, because it's going to be the 80-meter IF frequency and our BFO frequency. And if you recall, we had a center frequency of 9 megs, and now I've just notionally upped it by 1500, and same with our BFO, and that'll be our start point. We need a couple of variables here, so these top ones are all constants, they don't change, so we just set them here and compile it. Whereas these ones down here are actually variable, so or volatile. They'll be varied during program execution. So we need a variable to hold our old frequency. We need a variable to set our current frequency, which we will notionally just initially set it to be this value here, our start frequency. We need a variable to hold the radix, in other words, how much the frequency is going to change for each increment of the rotary encoder, and then just an updated display variable here, which I just use as a 1 or a 0. It's just a switch. Later on down here, if you can see down the bottom, we need to set up various pins on the Arduino to essentially tell the program that some pins are inputs, some pins are outputs, and to also set the internal pull-up resistors. It's quite common, rather than just writing down here pin mode, say 2 as an input, we would actually call that a name. So first we have to actually assign a name. So here we're saying here static constant integer rotary B pin we're going to assign to 3, and rotary A pin to assign to 2. So you recall that conversation we had before about the rotary encoder on the previous video. There goes those 2 pins there, the 2 outside pins on the side which has 3. So rotary encoder A and B notionally set to pins 2 and 3. And then that push button switch on the rotary encoder typically set on pin 4. Some more variables here that are used later on down in the program just for holding the state of what's happening with the rotary encoder functions. So just suffice to say there's some holding pins there. The next thing we need to do is we need to essentially initialize the screen and the Si5351. So we need to create those objects within the object-oriented code that C++ is. So here we are creating an object called LCD, and then for this Si5351, we're just going to call it Si5351. Now, this part here is of interest. You'll just need to make sure you know what your address is for your display. Interesting enough, you don't have to do that for the Si5351. It just seems to work every time with those Adafruit Si5351 breakout boards. I've never had to go delving into the library that supports the Si5351 to change any addresses. It just works out of the box, so to speak. Not so for the LCD display, or any display really, certainly when it comes to the I2C communications. Remember, both these devices, the screen and the Si5351, are in parallel. So there needs to be a way in which each of those devices know that it's been spoken to by the microcontroller or the Arduino, and that's done by an address. So in this particular case, the liquid crystal has 3F as its address. So once you've done that, you've created the objects, we can now go into the setup routine. Here we're telling the Arduino to what the various pins are, and rather than just having numbers now for pins, we've actually got sort of names which make it a bit more readable from a user interface from a software management point of view. So here we can say that pin A and pin B for the rotary encoder are inputs, as well as that push pin is also an input. We are enabling the pull-up resistors, so we want a digital write to those pins high. So that basically means that we're going to be testing in code for a low. So if any of the rotary encoders are not earthed, that includes the switch on the rotary encoder, those internal resistors will pull those pins high. So again, if you were to, for example, push that button on the rotary encoder, we would then be pulling this pin low, and that's what we'll be testing for in code. The next step is the interrupt pins, and this is the command that's used to essentially tell the Arduino that rotary pin A and rotary pin B, which we assigned to be pins 2 and 3, we want those to be interrupts. We want them to be triggered on change from either high to low or from low to high, and if that was to occur, these are the interrupt service routines, or the ISR. This is just a name that's been selected, and they coincide with, which we'll look at later on, actual functions. So these are the ISRs, or the interrupt service routines. So you need to essentially tie a function or a routine to an interrupt pin. Now, an analogy of an interrupt, imagine you're driving your car down the road. When the cell phone goes off, you should really stop the car, take the phone call, finish the phone call, and then start driving the car again. And that's essentially how an interrupt service routine works, or an interrupt. It interrupts the general flow of what the microcontroller was doing. So the microcontroller down here is just running around doing its thing. As soon as an interrupt comes along, it stops. It goes and executes the interrupt service routine, finishes doing that interrupt service routine, and then goes back to what it was doing. And we do that in this particular case to get that nice crisp frequency change when you rotate the rotary encoder, as opposed to you rotating the rotary encoder and there being a delay because the controller or the microcontroller was doing something else. So it's just a nice way of having a nice crisp change. So the next part of the setup routine is initializing the display, which is done through here. And once we've got the display up and running, so that's the LCD.begin. Now remember, this LCD and a little bit further down here, the Si5351, those are now objects. So these are the objects that we created up here. So there goes our LCD object there, which was based on that, and there goes our Si53 object based on that. So now we can execute, let's just call them sub-commands within that object. So we can now say that object dot begin, or that object dot backlight do something. And then once we've got the display up and running, we then tell it to run away and initialize itself. Well, not just initialize itself, update itself, and we'll see further down what that is. Small delay, and then we do the same thing with the DDS or the Si53. We initialize it. I won't go into these settings here. I'll talk about some of them, but there's a lot of information on the internet about how to configure this. I'm going to say I'm not an expert, but these are settings which I use over and over again, and they work well. So I won't talk about the phase lock loop, but I will talk about these two here. So these two lines here are quite important. You'll remember we talked about in the previous video making sure you set the drive level coming out of the Si5351 to match the mixer you're going to be using. Now I'm going to be using either the SBL1 or the double balance or the homebrew double balance modulator Again mixer in the next project. So they're a 7 dBm device, so I'm quite happy there to use 8 milliamps. So there goes the command there that the Si5351 library is expecting to see to set itself up. So for clock 0, which I typically use for the VFO, I want to be 8 milliamps. And for clock 2, which is typically going to be the beat frequency oscillator, I also want to be at 8 milliamps. If you're using that ADE1.1L, the low level drive, then that will need to be a 2 milliamps. And same with this one, I'm using both devices, both for the initial mixer and then the product detector. So we'll put those back to 8 for this particular example. And then we set the two frequencies. So we say for clock 0, go ahead and just send the frequency, and then for clock 2, send the BFO frequency. And this is required for this particular library, the times 100 ULL, just to keep things nice and happy. Rightio, we talked about the main loop and what that does. So it's just racing around and around in circles, just looking for either a change in the frequency or someone's pushed that push button switch. So I won't go into more of that one. Now those two interrupt service routines, now this is a bit of a caveat here too. Some of this program here is not my code. It is code that I found a long time ago. Initially when I was playing around with rotary encoders and the likes of the Si5351, had lots of problems with glitching, and you'd turn the rotary encoder and the frequency would jump to 3. It was really all over the place. I came across, I searched, typically as you do, searched the internet high and low, and came across what we were going to see sort of further on down, and I've stuck with it ever since. It just seems to work well for me, and I'm going to stick with it. So suffice to say, we have two interrupt service routines, depending on if it was the A pin that was triggering it or the B pin. And I am not going to explain what all this does, but suffice to say, this routine gets executed when that interrupt pin has a change. In other words, someone has been rotating that rotary encoder knob either left or right. Part and parcel of that routine is running this update rotary encoder function, which appears just below those two interrupt service routines. And here goes that particular function here. I think typically a lot of this code you see here in more modern, I don't say modern, it's the wrong way of putting it, in other libraries is hidden from view. It'll be hidden in a library, and you just basically ask the library, has something changed, and you'll get an answer back, yes. In this particular case, in my program here, the individual where I got this off, and I must admit I can't remember who it was or where it was, a lot of that code, rather than being hidden away in the library, is actually here in the main code. So it looks a bit confusing, and arguably it is confusing, but I will just say it works, and it works well. So of this particular function here, of what's of absolute interest to us, and the bit that we're going to play around with, and I do play around with many times, is this part here. So everything between that and that. So to interpret this, two things are happening. So when I rotate the rotary encoder knob, normally this second part of the function happens. If I'm rotating the knob to the right, I want the number that I'm currently wanting to change to increase. And that's what you see here. So frequency equals the current frequency plus the radix. And the radix, we'll see what happens. It defaults at the moment to 1 kilohertz or 1000 hertz. So that's what happens here. And then it does a test. If that frequency is now greater than band end, and you'll recall for this particular version of the software, I'd made that 30 megahertz. Therefore, it will then say, so if the frequency is now greater than 30 megahertz, frequency equals 30 megahertz. So if I was to turn that example hardware back on again and rotate the knob, I can't go beyond 30 megahertz because of this bit of code here. Now, the other option in this particular part of the software, if the digital read push pin is low, remember we talked about we test for low, so if that push pin is low, rather than increasing the frequency, I want you to increase the radix. And that's what this part here does. So it basically just moves the little underscore cursor left and right. So you can imagine if you're rotating, and I think I showed that in the last video, you push the switch down, you rotate the knob to the right, you expect that little underscore marker to move to the right. In other words, you're wanting to make the radix smaller. So that's what it's doing here. If the radix was this one, and now equals this, and say down here, if it was 1000, which is the default, it's now 100. So it's now changing in 100 kilohertz. So say again, 100 hertz steps, and then it rolls around. So if it was 1, then it flicks back around to the top. So those are the two options that can happen in this part of the code whenever the rotary encoder switch is rotated to the right. Conversely, we have the other option. The other part of the code further down, case 11, in this update rotary encoder function, is what happens when you rotate the rotary encoder anti-clockwise. And as you can imagine, normally the frequency now goes down. Frequency equals the current frequency minus the radix. If the frequency is less than the band start, and if you recall we set that at the very top to be 1 megahertz, it equals 1 megahertz, so you can't go below that. You're pegged at 1 meg. And then secondly, the other option, if that push button switch has been pushed and you're also rotating to the left, move that cursor to the left and also increase the radix at the same time. So when you do release the switch and you keep going in that direction, the radix here and just above us is what's going to happen. You'll see here this updated display equals 1, and there goes another one there. If we go back up into the main function, which is up here, the loop, which is sometimes called main in other programs or other software versions or software types, but the loop here, when I'm testing to see if the push button switch is low, I do an update display. In other words, I display that little underscore moving left or right. But what I do, I only do it once per click of the rotary encoder. I found if I didn't have this test here, the screen would flicker and it looked really untidy. So this is just a quick and easy way of, you've pushed the switch down, you've rotated either left or right, do one display update. There it goes there. Once you've done that display update, make that little switch there now at 0. That means next time it comes back through the loop here, it will not execute this because that's not true. Updated display is no longer 1 because it's 0. Now, further down here, during that time, if you were to rotate the rotary encoder one more click, either left or right, well then suddenly the very first thing that happens is you set that back to true or back to 1. So, back in the main loop, sorry I've gone too far, suddenly that test is now true and it updates the display again. So that's basically just how that works. It only does it once, it only does it again if you have moved that rotary encoder another time. That's all I'm going to do or talk about in regards to this update rot function. And then, yeah, so enough of that one. So then we're basically at the end of the program now. So the last part is update display. So we saw up there in the main part, or the loop, the main loop, a call there to update display. Now, this part here, this whole section here will change depending on the type of display you're using. In this particular case, I'm using that 16:2 display. So the first thing I do there is I set the cursor to 0, 0. So that is first position, first line, and typical sort of digital communications, it's 0 is the first line, and conversely down here, if we want to go to the second line, so there goes the first position, which is 0, and the second line down, or line 1, or line 2, called 1. First thing I do is I quickly just do a series of blanks, which overwrites what the old frequency was. I'd have to double check if that's still needed for an LCD, but certainly in other displays, that's quite a useful thing to do, to just overwrite what used to be there. I then make sure the cursor is back to the starting point again, and then I print the frequency. I then move to the 10th position and just put the old vanity call sign up there, or anything you want. I then go directly down the line, so same 10th position, but now down the line, and just something else to print. This is all just all arbitrary stuff. You can do whatever you like here, and in this particular case I've just put 80 meters. If you wanted to, that could be the radix if you're so inclined, or it could be transmit receive if you're sensing that, whatever you want. I then go back to position 0, or the start of the screen, on the second line, which is the 1 there, and I just blank out whatever was there. I then reset the cursor back to where it was, and then I do a test, and then I print that little underscore. That's that little thing there. I didn't show in the last video, but you could imagine if the frequency is greater than 9.9999, in other words, you're now into 10 megahertz and above, you need to step the whole frequency you're displaying one position to the right, because you now need to display the tens of megahertz. So that's what it's basically doing here. It's just testing to see if you need to start drawing those little underscores either at the first position or one position to the right, depending on what the frequency is. So that's basically what this little if function here is doing. So if the frequency is greater than that, in other words it's 10 megahertz and above, this is where I want you to put the underscore depending on what the radix is. And conversely, if the frequency is less than that, it should actually be less than or equal to, so it should have equal signs there, then I want you to, this is where you need to put it. So just a little bit of formatting there. This is exactly formatting. Right, and that really is, in such a simple little display as this, all that's in the update display. If you had an LCD, you know, the 320 by 120, or, you know, a much larger display, then, you know, your world's an oyster and you can do whatever you like. But I'm just displaying the bare minimum information on that little 16 by 2 display. And then the very last function here is, I'm not going to say where the magic is, but this is the function that sends the commands to the Si5351 to basically update itself. So first thing here is the VFO. So that, remember, that's clock 0. So here we're saying here, and now you just need to cast your mind back to the drawing we had for the crystal filter. We're doing up conversion, so we need to work out where we are going to place that local oscillator, or the variable frequency oscillator. So we start with our IF frequency, which you'll recall was just sitting on the high side or just above the pass band of the crystal filter. So 9001500. So we start with that. We subtract the frequency we currently got, and that little 70 there is a fudge factor. And I'll come back to that. So once you've done that, you then say that's where the variable frequency needs to be in order to mix with the incoming RF and place the IF and the intelligence just on the high side of the crystal filter, so therefore our desired lower sideband is sitting inside the passband of the filter. So that's basically all done there. Now if you're doing down conversion or any other type of scheme, then this is the part of the program where you would make those changes. So that may be, there are cases where I have, that would be a plus, and you'd put on the high side. So the variable frequency oscillator will actually be above the intermediate frequency. But suffice to say, this is where you do all those manipulations to make sure that the VFO is sitting in the right place. We'll come back to 70. And then with the beat frequency oscillator, remember that's fixed. So there's no frequency function in here. That's just set hard in this particular case because we defined it at the very top at 9001500 hertz. And that's just set, and that's coming out of clock 2. Now this 70 here, I talked about that 1500, so that center frequency plus 1500 hertz is a rule of thumb. It's a bit of a starting figure, and that's exactly what it is. So you start with that, and what I typically do then is I do subtle adjustments down here to make either the reception sound spot on for the desired receive frequency, or on transmit, if you're doing a transmitter, that the transmitted signal sounds nice on a secondary receiver nearby. So it's just a fiddle factor, a tweak, whatever you want to call it. And I just leave it down there in all its glory, so I just know what's going on. You might have seen in the previous build, I had a piece of software running on that last radio called a BFO tuner, where I could individually tweak the values to make things sounded right, and it would actually display on the screen a number which is exactly that one. So it would be the number that I then need to feed into the main software to make everything sound nice, and that's what I do there. Right, so that's been 34 minutes, so it's quite a long video, and I apologise for that, but hopefully that provides a bit of sort of insight into how I do things. And as I mentioned before, it is not the right way, it is a way. It's a way that works for me, and it's a way that I'm going to stick with for the foreseeable future because it just works. Any questions, please sing out. Displays, I will just say displays are the biggest bugbear when it comes to a lot of the software engineering I'm doing here for these sort of simple radios. I've got all sorts of various sort of cheap screens in the box, and honestly trying to find the library and, more importantly, the right address to talk to them can be sometimes a real pain in the backside. But yeah, enough said there. Okay, I'm going to knock it on the head there. Any questions, please sing out. And like I say, if anybody wants this code, I shall put it up on the blog, and people can use their heart's content. I am not going to claim ownership to all of this, and I wish I could remember where I got the original sort of ideas from to give credit to that person. But there you go. Anyway, 73s, thanks so much everybody, and I'm away for a little while, and when I get back, I think we'll put a video out looking for some ideas on the next build. I talked about that on the last, or a couple of videos back, when I sort of wrapped up that last one. It's just more around just sort of thinking what I want to do or how I want to present it to be useful for others. It is my build, but at the same time, I'm quite keen to at least pass on what little knowledge I have to help others to try and do the same thing. And that's really the whole aim of doing the videos in the first place. Anyway, 73s. Any questions, sing out. Otherwise, we'll see you in the next one. Cheers all.